Okay, so it seems like it's the time to start the meeting. So hello, everyone. Welcome to the meeting of the 6LO Working Group. My name is Carlos Gomez. The other chair is Shweta Bandari, and our responsible AD is Eric Klein. We're all here. And for minute taking, we have Dominique, who has kindly volunteered. And thanks a lot, Dominique, once again. And nevertheless, we encourage everyone to join the collaborative process of taking minutes. So don't hesitate to join the link that you can find at the end of the slide. Next, please. So this is the notewell. This is a reminder that if you are participating in the IETF, then you agree to follow the IETF processes and policies. The notewell contains a number of pointers to documents on several of these policies, so please make sure that you have read it. Next, please. So this would be the agenda for today. The first presentation is the usual chair's introduction that's currently in progress. This will be followed by the presentations given by Pascal, entitled ND Multicast Address Listener Registration and ND Unicast Lookup. This will be followed by a presentation on the updated version of the draft entitled Transmission of SHE Conference Packets over 15.4 networks. After that, there will be a presentation by Luigi Iannone entitled Native Short Addressing for LLN Expansion. And the last presentation will be given by Hao Yu Song, entitled Short Hierarchical IP Addresses at Edge Networks. So as you can see, this is a packed agenda. So we hope the presenters can stick to the allocated time. And also, as in the last IETF, we're going to dedicate most of the session to presenting and discussing new materials. So is there any comment on the agenda? Okay, so if there are no comments, then let's proceed to the next slide. So regarding the working group documents status, we have one document in the RFC editor queue. That's the IPv6 mesh over BLE links. Then we have two documents that have been evaluated by the ISD. The first is IPv6 over NFC. And this document was evaluated the first time by the ISG a couple of years ago. Then it was updated after some time. And in the last IETF, there was some conversation about whether the NFC specification would be available to all the intended participants. So I don't know if perhaps Eric Klein, our AD, would it be possible for you to give some update or some suggestion about the next steps for this document?
Yeah, I received the NFC specification. I think I haven't had a chance to go through it. I went through some stuff that was publicly available, but I think the broader concern that the ISG chair had was basically, how do we communicate that everybody who needed to read the details of the spec was able to read the details of the spec when the working group was drafting the document, or when it was in last call. It might suffice to just have a reference to BCP 97 or 97 bis or something in the Shepherd write-up, or I don't know. It's on me to close on that issue with Lars. So.
Okay, thank you. Then the next document that has been evaluated by the ISG more recently is IPv6 over PLC. So there are at the moment 3 outstanding discussed ballots, and there were several comments. The authors have a plan to submit a revised version of the draft in roughly 2 weeks, and at the moment have already replied to most of the comments. Then the next document is 6LO use cases draft, which passed the second working group last call. So the next step will be getting the Shepherd write-up. And finally, we have a new working group document entitled IPv6ND Multicast Address Listener Registration, which was adopted very recently and which had pretty good support. And by the way, this will be presented later today. So is there any other comment or question? Okay, so if there is no comments, then I guess we can proceed to the presentations by Pascal.
Do you wish to share? Yes, that's nice. Are you going to move the slides, or can I do it myself? I don't know that I can do it, but maybe I can. Shweta, you will be the one advancing the slides for me?
I'll navigate the slides.
Okay, please. Okay, so please, let's start. Next slide, please. Okay, this is a generic intro for both documents that we'll present today. So as you know, we now have a family of documents around 6LoWPAN-ND, and it's getting proposed and used in environments which are way beyond the IoT right now. Initially, the focus was on wireless. So at some point, we called it WIND for wireless ND. But now we are proposing it for Rift. We are proposing it for EVPN. So it's way beyond wireless, and wireless does not. And the wireless in the title does not really help understand what this is. So recently, it's been proposed to call this family of protocols IPv6 stateful address-to configuration, as opposed to IPv6 stateless address-to configuration that we know very well. So the family starts with 6775, which was extended updated by 8505. More recently, we published address protection for it, meaning that the address that is advertised by 8505 can now be protected against address theft and impersonation attacks. And we have 8929, which basically specifies how to proxy neighbor discovery when you have a network where you have legacy ND and 8505, which coexist. And the most classical example being 8505 on the wireless and 8929 on the wire. But it can be any other composition of network. And now we have two new documents which are being proposed to this group. One is still personal submission. I will discuss it next. And the one that we are talking about now is the multicast registration. So as you know, 8505 was about unicast IPv6 addresses. And so you could not register multicast. And if you did register anycast, there was no signaling to say, hey, I might not be the only one who wants this address. And this could create confusion in the routing, and only one node could possibly win. And that prevents the use of anycast for load balancing purpose, for instance. So we have this new draft. Next slide, please. Which is the draft IETF 6LO multicast registration, where we enable 8505 for not only unicast IPv6 addresses, but now anycast and multicast addresses as well. And if you consider the position of an IoT device, in an LLN device, a 6LN, being able to register that is a listener for a multicast address saves the need to implement MLD. And as you know, MLD is expensive in terms of energy and wireless resources because it's based on broadcast. The same reason why we designed 6LoWPAN-ND in the first place to avoid broadcast is also the reason why we want to avoid MLD and use X8505 for multicast and anycast as well. The benefit is that the 6LN goes mostly unmodified. I mean, all it needs to know is, yes, I will accept packets for those anycast and multicast addresses as I would accept packets for my anycast addresses. And I won't use them as source. That's pretty much, all it needs to know. And we validate that it knows that because when it registers a multicast or an anycast address, now there's a new flag associated in the ERO. and actually in the IDAR message as well, to signal the address is unicast, anycast, or multicast. There's more work on the 6LR side, because now it will accept more than one registration for the same address. And so for anycast and multicast address, the index for the registration becomes the combination of the address as before and the rover field, which is the basically the information which is used to uniquely identify and validate the ownership of the address. You'll find when you read the draft, if you've not done so yet, that we also do some REPL-related work in this specification. We did not want to do like 8505 and 9010 two separate documents, because that would take too much effort to just make sure they are synchronized and, in terms of content, and take them separately through all the ISG process. So we kind of decided to make a unique, consistent operation between what 6LoWPAN does on the 6LN to 6LR hop and what REPL will do on the rest of the network. So we also specify the REPL piece. And for that, we extend RFC 6550, in particular with a new mode of operations. For those familiar with REPL, REPL has a number of modes of operation. One of them is just a tree where you can report data but not get data back. The collection tree. Then you have non-storing mode, which in case of IoT is the most currently deployed, whereby the route does source routing down the DODAG to the devices. We have a storing mode with multicast, and more recently we have introduced AODV, which could be MOP4 or MOP5 actually. I'm sorry, MOP5. Well, MOP4 or MOP5. We hope it's MOP4, because MOP4 was just an experimental RFC so far. And if that's MOP4, that means that we free MOP5 for the new non-storing multicast mode that this specification is introducing. And for anycast, there was strictly nothing. All we said for anycast is, if you inject the same addresses at multiple places in the network, you should use the same sequence counter. And now we are giving explicit information about how you do anycast in the existing MOPs, and including the new MOP that we are defining here. Next slide, please. So this tells you a little bit more on the new REPL MOP. We'll discuss more the REPL side at the role meeting. So if you're interested in this document and this multicast operation for LLN, I invite you to also attend the role discussion later on this week. I think it's Wednesday. So the 6LRs, as I said earlier, they have a little bit more to do. First, they need to accept more than one registration with different rovers, and they will not consider them as duplicate. They have to pass the new flags saying unicast, multicast versus anycast in the ERO, and turn that into DAO. In the REPL target option, now we have the same flags for anycast and multicast, which have to be set, and as the 6LR injects that into REPL. With the new mode of operation, the DAO from the 6LR flows all the way to the root, just as if it was an external destination, a REPL unaware leaf. And so the multicast or anycast packet back can be tunneled to the 6LR with exactly the same tunnel as if it was a unicast packet to a REPL unaware leaf. The 6LR decapsulates that packet, and instead of a unicast IP packet, it will find anycast or multicast, and it will route them appropriately to the 6LN. Packets which are generated inside the DODAG, since the only route, the only route in the DODAG is default towards the root, they will just follow the path to the root, and it's the root which will effectively find that it's multicast or anycast and do the appropriate processing. If it is a multicast, it will perform ingress replication, meaning that it will make one copy per 6LR, which has listener, at least one listener. for that multicast. So a number of the 6LRs will get a packet over their tunnel and decapsulate and forward to their 6LNs. Each 6LR registers only once. I mean, it just injects one in REPL, meaning that the root will have to distribute one packet per 6LR, and it's the 6LR role to distribute multiple copies to the 6LNs. For any cast, instead of passing the packet to all the 6LRs, it will pass it to a select one, and we don't effectively say in the specification which 6LR. I mean, the policy in the root may depend on a number of things like load, and this specification does not enter this configuration, just says the root can select one, and further specification or implementation will decide which one. Next slide, please. So as I said, the 6LR is modified. More than one 6LN will register. Actually, the 6LBR is modified in the exact same fashion. And as we extend the ERO to add the A for anycast and M for multicast flags, we also change the IDAR message to carry those flags. And by the way, we do that using the status field, which is the only field that was still free in the IDAR message, which was used for the IDAC, the confirm, but not for the IDAR request. So now for the IDAR request, we set the flags in the same byte, actually, that will be used for the status on the way back. So 6LR and 6LBR must retain all registrations and index them by tuple registered address rover. As I said, they will inject the addresses in REPL. That can be any of the existing modes, including, and that can be the new mode. If it was mode 3, which is storing mode with multicast support, we actually extend that mode to say that the flag must be set for multicast if it's multicast, or anycast if it's anycast. And for anycast, we specifically indicate what the new behavior is, which is you select one of those children and only one. For multicast, you basically make a copy per child in storing mode. On the way back, when the packet is received from the parent in storing mode and from the root in non-storing mode, the 6LR decapsulate if tunneled, looks at the packet, and now it can be anycast or multicast, so it will find possibly more than one registration. If it's anycast, it will select one. Again, we don't say by which logic, which policy. And the only thing is, if the packet, if it doesn't manage to send that packet to that selected 6LN, it still has the opportunity to select another 6LN which listens to the same anycast address. And after some retries, retry to this other 6LN. For multicast, the goal is to deliver one copy to each child. And in radio networks, radio LLNs, typically it is more reliable to do a unicast replication. That means send a unicast layer 2 packet, layer 2 frame, containing the multicast packet to each of the 6LN one by one. Next slide, please. So there's a lot of consideration about backward compatibility. This document, this specification, was done by the explicit request of YSUN, which is one of the alliance which use 6LO specifications. And they were effectively in need of having a support for multicast, and they needed a spec from the IETF to cover it. They were very pleased that we proposed something that does not entail supporting MLD. And so, as is the case with 8505, even for multicast now, the device can live without any MLD at all. But there is a lot of brownfield, there's a lot of deployments of this alliance specification that will need to be incrementally improved with support of multicast. So there needs to be compatibility and deployment considerations regarding mode of operation 1 in particular, which is deployed throughout. So basically what we say is, yes, you can deploy this specification in a brownfield with MAP1, but the devices will have to know whether a 6LR supports this specification or not, and only send multicast registration to 6LRs which do understand it. So we added a flag in the 6CIO, the capability option, to indicate that the 6LR supports this specification effectively. And there is also some text in case the 6LBR does not support it. So we can still operate if the 6LBR does not support multicast, which is seen by the fact that when we register multiple multicast address or multiple anycast address, multiple times the same anycast address, the 6LBR will say duplicate, duplicate, even though we signal it's anycast. So in that case, it really means that the 6LBR does not understand the signaling of anycast and multicast. And so that's how the 6LR can know that the 6LBR, there's no point in doing the EDAR with the 6LBR because it will not understand it. So at that point, it can stop doing it. And we also described the incremental operation with MOV3. Next slide, please. Actually, there's one last thing I did not write in there is the routing doesn't have to be a REPL, right? There can be all those routing protocols we already support. And as I said, we are already working on using 6LoWPAN-ND in EVPN at the BESS working group. They will be presenting at BESS about that. And so we basically want to ensure that what we are, the UNI interface that we are defining between the node and the router can be used for any routing protocol, including BGP in the case of EVPN. And so we in the one hand, will be extending those other drafts to support multicast. And as well, we are also providing already some other integration in this specification. And we discuss in particular the use of MIPO, which is also quite used in LLN. So we basically say, hey, you can use the new mode of operation for non-storing multicast, even if the routing for multicast is not REPL, is not this ingress replication by the root. Instead of doing this ingress replication, you can, for instance, use MIPO to as you know, it's a flooding mechanism to flood the multicast message, and then the 6LRs will get their copy and they will do as if it was received out of the tunnel. Voila. So yeah, this is a very recent document. We are actually trying to work very, very swiftly on this one because of this external alliance, which needs it, you know, as soon as we can deliver it. So we are proving actually that the IETF can deliver a spec in a fast pace when that's really needed by our partners. So far we are doing good, and I hope that we'll get some reviews soon so we can progress the document. So reviews are welcome, and please think about doing them quickly because we want to have a very fast turnaround on this one. Question, feedback? I'm not seeing questions.
Yeah, perhaps one comment would be that, as you mentioned, well, it would be good if we could have a couple of volunteers to review the draft. There was already some discussion on the first versions of the document, but anyway, it will be good if we have a couple of reviewers. So if anyone wants to volunteer, please let us know.
And implementations as well, if I may say. I see Adnan, for instance, in the list. Yeah, if somebody could look at trying this on one of the open source implementation of 6LO, that would be really, really nice because we could get, you know, firsthand commenters' feedback.
Pascal, one other question. Do we have to share this with other work groups who might have feedback on this as well?
There will be definitely a sharing with ROLL because I'm presenting at ROLL. And at some point, we'll have to ask our ID to synchronize with Alvaro Retana, who is the routing AD in charge of ROLL, to figure out how we progress this document. The idea was so far that we progress it at 6LO, but we must have reviews by ROLL. And so at some point, I guess there will be maybe a last call or something at roll as well. Something to ensure that roll is fine with this document, because we are defining a new mode of operation for REPL in this specification. So it cannot be done without, roll contribution.
I was chatting with Alvaro, and I think he said Pim might also be interested in this, so he requested that Pim get notified.
Pim, okay, neat. I didn't think about it, but yes, REPL builds a tree for multicast, which is REPL storing mode, which is very, very akin to a PIM tree, very akin. For the ingress replication that we're introducing here, it's more like what EVPN does, actually. Any others? Okay, let's move to the other spec in the interest of time. So next slide, please, Shweta. So this now is a quite ancient document that we tried long ago. Story goes that when we did 8929, we realized that now there is, on the Ethernet side, there is this knowledge of, at least a partial knowledge, of the address mapping for at least some of the addresses, mapping of MAC and IP address, which can be used to reply to an NS lookup. For all the addresses which are registered to the 6 LBR, the 6 LBR could definitely answer as a unicast request response exchange to an address lookup, as opposed to doing the multicast NS lookup that you all know ends up as a broadcast on your system. So yes, it only works if the address is registered. Otherwise, basically the 6 LBR needs to say, hey, I don't have this registration, so if you have any other way. But at least it can be tried as a quick first try before the lookup, the actual lookup is done. You might realize that the 6 LBR is really abstract. It can be implemented as a BGP EVPN network. For instance, in the case of the EVPN draft, you realize that the whole BGP database is effectively the 6 LBR, so it's completely distributed. On the other hand, it can be implemented as a Lisp map server map requester, MSMR, in which case it's, it appears as centralized, even if, just like DNS, it can be something complex in the backend. So the 6 LBR is really a conceptual object. What we do with those RFCs is we just provide a handy type of messaging to talk to the 6 LBR. And so far, it was used mostly to provide duplicate address detection. That was the goal in the original RFC 6775 of a whiteboard where we can write all the existing addresses. So if there is a duplication, we can see it from that board without doing broadcast. Well, with the draft that we are talking about now, we are also enhancing the 6 LBR as being a registrar that you can query for address lookup. And when that works, well, you have a very fast and unicast, that's read the value, unicast exchange to get your address sorted out, your mapping sorted out. And as you know, that's pretty much what happens in a modern fabric right now when you go to a Lisp MSMR and request your mapping. And that's what happens as well, but proactively when EVP and BGP exchange the route tab 5, where you can actually have this mapping as well. So basically, asking to your 6 LBR what's the mapping is pretty much asking your router, which does EVPN, what's the mapping, because he has that information. In the case of EVPN, the router will use it itself to encapsulate in the VXLAN. But actually, you could consider a very same fabric where you don't effectively encapsulate. You just ask the router, hey, give me this mapping. I will use it right away on a flat fabric. Next slide, please. So this is, like I said, a very old draft, which was published, when we kind of were finishing the backbone router document. And we just realized, hey, instead of having 6 LBRs all across the networks, for instance, within the Wi-Fi access points, you could actually consider it as more abstract and centralized on somewhere on the backbone. And if you do that, then anybody can query it. And that's pretty much what this document is doing. to be able to query it, we needed the SLLA option in the EDAR message, because that's usually how the 6LR, which would be all the access points, are talking to the 6LBR, which is now centralized, virtually centralized. And that addition was already done with 8929, so we don't even need to specify it. 8929 already said, hey, you can transport your ND options in the EDAR message. So now we are actually leveraging that, because through the EDAR EDAC or through the NSNA exchange, the 6LBR will be aware of the mapping, and you can query it either on the local link using NSNA or even from remote using EDAR EDAC to get the address mappings. So we started the draft at 6LO 2 years ago. There was this comment that it's mostly for the Ethernet side, so maybe you could try with 6-man. So went to 6-man, tried and failed to raise interest. And that can be explained by the fact that we are not maintaining an existing protocol, which is really the specialty of that group. But we are creating really something new, which is based on work which was done elsewhere. And so, I mean, we never really caught up at 6-man with any of this work. And so it's not a big surprise that after 2 years, we can say, hey, we tried, but you know what, we didn't raise interest. So let's come back to the root and do the work at 6LO. That's pretty much the proposal. I think I have next slide, Shweta. Yeah, so it's basically what I said, just summary of the operation. So now you can think that the 6LBR is virtually centralized on the backbone, and every information that is available to him, which is all the address mapping that were registered, can also be queried by anybody on the backbone, or even further than that. And for that, we leverage the SLLA option, not only in the NSA, but also in the EDAR EDAC exchange. And by the way, we provide this new message, which is similar to EDAC, but the code, the type is the same as EDAR EDAC, but the code is incremented to say, instead of saying address duplication, remember EDAC is duplication DAD, basically. This becomes address mapping, so it's code 1 instead of code 0, code prefix 1. And it really means address mapping, so you can use it to query an address mapping and get a response back. And that's it this time, Shweta. Thank you. Don't think I have a next time. Oh, yeah, so yeah, there we go. So, yeah, I can improve it a little bit. Then I would like to see if we get support in this group to continue this work.
Thank you, Pascal. I don't think we have time for discussion. Maybe we should take it on the mailer. We should move on to the next presentation, which will be Carlos.
Okay. So hello again. I'm going to present the updated version of the draft entitled Transmission of SHIC compressed packets over 15.4 networks. My co-author is Ana Miraburo from Aclio. Next, please. So first of all, as a quick reminder of the motivation for this draft, as the working group knows, RFC 6282 has been the basis for header compression in 6LoWPAN and also in 6LO. It was designed for 15.4 as the target technology below IPv6, and it has been adapted or reused several times for relatively similar IoT technologies for which IPv6 support has been enabled. And well, last year there was the publication of RFC 8724, also known as SHIC, which is a product of the LP1 working group. SHIC defines adaptation layer functionality, and it includes a header compression component. So SHIC has been designed for even more constrained technologies, which are such as LP1 technologies. And for that, the header compression in SHIC is more aggressive than the one in 6LoWPAN. The trick is using static context based on a priori knowledge of header field values. So next, please. So we can give some numbers on the performance that we can get. And we may compress the headers of IPv6, UDP, and CoAP down to 11 bytes by using the traditional 6LoWPAN or 6LoW compression, whereas we could reduce those headers down to a size of only 2 bytes with SCHC. This is for both mechanisms, assuming the best case global addresses and no co-op header options. So for battery-enabled devices, this may represent some theoretical battery lifetime improvement when those packets ascend over 15.4 by up to roughly 40%, even if we include an additional third byte, which would be the SCHC dispatch, as will be shown later. Although a disclaimer here is that the actual improvement will be lower, depending on various parameters and features, such as the device hardware, including the sleep state current consumption, MAC layer and application layer settings, payload size, and so on. Next, please. So this document is related with a previous document that tried to define a 6LoWPAN dispatch type for SCHC. However, this document has a greater scope. It tries to provide all the details needed to enable the transmission of SCHC compressed packets over 15.4 networks. So today I'm presenting revision 01, which provides some new content and improved structure, and it aims to incorporate the feedback from the last IETF. Next, please. So on the updates in 01, here you can see a div of the table of contents. So you can see how the two main sections in the draft, section 4 frame format and section 5 SCHC compression for IPv6, UDP and co-op headers, now are more detailed and more complete. Next, please. So in section 4, we define the frame format. What you can see, the figure on the slide corresponds to the 15.4 frame payload when a SCHC packet is carried. And the leftmost field is the SCHC dispatch. So in this version of the draft, we would use a 1-byte pattern from page 0. The one that's suggested is the one written here to be confirmed by Ayana. And this is better than the previous approach where we attempted to allocate a whole page for SCHC. So this is better in terms of making a more efficient use of the existing 6LoWPAN dispatch type space. So this byte here is one of the not allocated ones currently. Okay, so the SCHC dispatch signals that what comes next is a compressed SCHC packet, and the next field is the SCHC header, which comprises a rule ID and, if any, a compression residue. So in this version of the draft, we state that the rule ID size is 8 bits. Next, please. Then in section 5.1, we specify how IPv6 UDP header compression is performed. We state that it must be performed as per section 10 of RFC 8724, except for one thing which concerns IPv6 addresses and UDP ports. In the base SCHC specification, RFC 8724, there are two terms, deb and app, which are related with the underlying architecture that's assumed, where there will be devices like, for example, sensors, here abbreviated as deb, and some application, which might correspond to some entity in charge of centralizing data collection on the network side, here abbreviated as app. And these two terms allow to use a single rule in both directions. So there's no need to have one rule for compressing when we send in one direction and another rule for the other direction. However, the problem here is that in 15.4 networks, these two concepts do not always apply. For example, when the two endpoints that are communicating are in a mesh network and are of the same category. So for this reason, we state in 01 that if an IID is based on layer 2 header fields, then we don't use the compression decompression actions called deb IID and app IID. Instead, we use compute IID. And then there's another consequence, which is that in the base SCHC specification, the terms uplink and downlink are defined by using deb and app. So if deb and app do not always apply, the same happens with uplink and downlink. So perhaps we may want to use new terms, at least in some cases, which could be transmit and receive, as is in version 01 in this document. Next, please. So we also have some initial content in the security consideration section because the document does not define header compression functionality beyond the one in IFC 8724. We state that the security considerations of the corresponding section 12.1 from the basic specification apply. And also we add that as a safety measure, a SHIC decompressor must not reconstruct a packet larger than 1500 bytes to avoid some type of attack which might want to overload the resources of the receiver, the decompressor. Okay, next please. So that was everything from my side. I don't know if there's any comment or question. Yeah, Dominique.
Yeah, thank you for the presentation. I have one question. What's the reason for choosing that the rule IDs will be 1 byte? Why do you need to specify the rule ID length? And is 1 byte enough?
Well, admittedly, this is a bit tentative. So, yeah, it seems like, at least for the use cases that we were considering, 8 bits seem to be suitable, seem to be enough. Although this is actually open to discussion. So if there is feedback on this or some alternative ideas, we are open to discuss this.
And the first part of the question was, why do you need to specify the rule ID length here? Why can't you leave it open?
Yeah, that's another point. Yeah, it seemed, for the moment, it seemed like specifying this might make maybe implementations more simple. Perhaps it would be enough, but yeah, maybe we may want to have some additional thoughts about whether we might want to have some maybe unspecified size for the rule ID. Okay, Pascal.
Yes, I was wondering. Yes, this point that you made about device to device, basically, when you, I mean, I'm a bit anxious about this deriving from IID, and it doesn't seem too fair to find out that you need to operate in a mode symmetrical or non-symmetrical based on address. I'm still a bit confused by that. I hope we can discuss and find something a bit different. But the core of my question is the LP1 architecture. We are writing in this architecture that you have both cases, effectively, as you described, the asymmetrical and the symmetrical kind of modes. And I just wanted to make sure that what you are presenting here is completely covered by the architecture. Otherwise, we probably need to adapt the architecture to make sure that what you describe, what you need is also there. So yes, basically, I was asking, can we sync this document and the architecture, make sure we have the full story? And this story of IID doesn't look fair.
Okay, then we'll, yeah.
I mean, if you were talking about Bluetooth, we could say, hey, kind of easy, right? If you talk to the central device, then probably you can be asymmetrical. Or if you talk device to device, it would be symmetrical. But because you know who is your central device, but in 15.4, you don't know who would that be. Maybe we could just say symmetrical by default. Do we really need this optimization of being asymmetrical?
Okay, yeah, so we'll discuss this and consider it for the next update. Thank you. Thanks a lot.
I think any further questions, we can take it in the chat and on the mailer. Moving on to Luigi's presentation.
Yep, I'm here. Okay.
Thank you.
Thank you. I'm going to present in the next 10 minutes or so an update about the native short address draft. So slide. Next. Yeah, thank you. So there are a few things that are new in this document, including me as a co-author. I'm not the only one that joined the effort. There is also David Liu, Peg Liu of China Mobile. One important thing is the fact that actually the document changed name. So this is a revision actually, but still numbered at 00. The title is now Native Shore Addressing for Low Power and Lossy Network Expansion. Just to be clearer from the title of the scenario to which this document applies. Okay, and we also spent quite some effort in try to detail the scope of the document, because this is, as I said, is about LLN, but with fixed geolocations. So the kind of mobility that we can have in this kind of networks is mostly related to radio connectivity, not physical mobility. Okay, next. Okay. For those who knows the content of the previous version, there is one section which is the Nsa allocation. So basically, how we create the addressing of the different nodes. So the allocation function that does that specific action has been better formalized, so that is a little bit clearer to understand. And most importantly, we added a step-by-step example so that we really can see how to build the addressing and how it works. Yet, at the same time, the allocation function is open to be modified if someone wants to. Okay, if by any reason it finds something that allows you to improve one aspect of the other, the specs now allow to, let's say, upgrade the allocation function. And we also added further clarification about the NSA addresses itself, how they interwork with IPv6, and how what happens with the width of the routing tree depending on the topology that we have. Slide. We refined also the description of the routing mechanism, because depending on how the addressing allocation is done, then we have actually a very simple way to do the forwarding, because we basically look at the length of the address and we take a decision. So if the address is shorter, it means I have to send it up in the hierarchy of the tree that we are building. If it is the same length, I ask, I'm the destination, yes or not. If not, I send upwards. If the destination has a longer addresses and is in the prefix of a certain node, it sends it downwards, let's say. So we better clarified everything, every step, and we added a flowchart that hopefully helps in understanding what all these operations. Next. We revised a little bit the communication with external nodes. So when we go beyond the root of the tree that NSA is building, and we want to communicate with the IPv6 destination, basically. So there is an important distinction to be done. One is when someone external wants to contact a certain node. So, but by in that case, it is easy to set up the communication, because at the very end is the root that decides a mapping between the external IPv6 address and an artificial NSA address that is used to map with the external. The other way around needs more work, in the sense that if an internal node wants to contact an external IPv6 address, this decision is made locally by the node, right? But the mapped NSA address of this external node has to be decided by the root. So what we do is we send the first packet with a full IPv6 address. The root takes a decision and sends back a message, specifically an ICMP v6 message, in order to tell the node this for next packets to be exchanged, you can use this short address. Okay, next. The usual stuff in a certain way when you revise a document is to polish the text. We try to polish also or simplify the various figures that are there, and I better highlight the benefits that the NSA format introduces. The IANA section has been completely revised. I mean, this is in line with how the IANA consideration section should be written. So we are asking for some registry, and we start to populate the content of those registries. Next. So this is the result, obviously, of us, the co-authors, but with the help of different people with which we had interaction, and we wanted to thank them all for helping us to improve the document and pinpoint some issues that we tried to address. Okay, and so thank you. But further feedback is always welcome, obviously. Next. So this is the final slide. We did quite a thorough work, and we are going forward. So the last slide was about the authors think that the document is stable and maybe could be considered to be adopted as a working group item, yes, to be discussed. I don't know if we have time now, but certainly maybe later on the mailing list. Thank you. I open for question if time allows.
Yes, so perhaps there's not much time, but there was one point that raised some concerns in the previous presentation in the last IETF about the renumbering and so on, when there was this dynamic in the network with links changing and so on. So it would be good to see whether the people who had concerns on this may have any comments. So yeah, perhaps it will be good to have some discussion on the mailing list about whether the updates address those concerns.
Yeah, we proposed a solution. We certainly can discuss more on the mailing list, knowing that we consider a rather static scenario. But anyway, absolutely, discussing on the mailing list to check whether the issue is considered solved with the current revision is something that can be done. And I guess Pascal is asking to comment on that.
I'm not being told that I can speak, but since nobody's speaking, yeah. If you tell me, okay, the applicability is all the network is built on 8-port switches, Ethernet, and you know exactly how many ports you have, and the wires will prevent you from trying anything stupid. So yeah, that will work. So if you give us an applicability statement, this is for exactly this network, where none of the issues, and there are multiple ones which kill data to the 15.5 and other stuff, apply, then yeah, why not? But you need to be very, very specific on where it applies, because generally speaking, it won't work just the same way 15.5 didn't work. And so you have to provide that. I mean, yes, if you say 8-port switches only, I'm okay. I'm done.
Okay, I mean, we did provide text to specify the scenario, but we can certainly have more iteration through the mailing list and see if this is sharp enough or should be improved. That at the end of the day, this was our intent, to clearly shape where this solution can be applied.
Okay, thanks. So
thank you very much.
Thank you. So we are a bit running out of time, so we may need to proceed to the last presentation and continue the discussion on the mailing list. So yeah, now we proceed to the presentation by Hao Yu-song.
Hello, can everybody hear me?
Yes.
Hello?
Yes.
Yeah, okay. This is Hao Yu-song from Future Technologies. Today, I'm going to talk about our new draft on using short hierarchical IP address and edge networks. Next slide, please. Okay, so we all know in the IoT networks, the entity communication are highly sensitive to overhead and energy. But on the other hand, we know the IP this overhead is due to part of it is due to the heavy IPv6 overhead due to the long source and destination addresses. But meanwhile, most of the communication happens in the edge network actually between adjacent and related entities. And they share the same IPv6 prefix. So the key observation is why should the entity know the prefix at the first place? Next slide, please. So if we observe the address, we can see the entity in the IoT network will share a common IPv6 subnet prefix. And below that, if we further partition the network into multiple levels, then each level will own its own network ID. And finally, the entity ID is only part of the suffix of the IPv6 address. So therefore, our key idea is let the entity only know and use its own entity ID. And while we delegate all the network ID and the prefix maintenance and operation to the gateway routers. Next slide. So therefore, for the address part of the packet header, we can only maintain the length of the source address and the destination address, followed by the two variable lengths, the source address and the destination address. In this way, we can really compress the address part of the header. And for the network architecture, you can see we will have multiple levels of the subnetwork, and each level will have one or more gateway routers. We call them level gateway routers. So the network prefix for this level of networks is only maintained by this gateway router, while other entities in the network will only know its own network is a node ID. And there are some other type of routers called intra-level routers, which are responsible for packet forwarding within the level network. Those routers are, they don't maintain any prefix within them. Next slide, please. So here is an example of a network. You can see the external networks in the IPv6 domain. It allocate 96 bit prefix to this edge network. And within this edge network, it owns a 32-bit address space. We can further partition this network into multiple levels. On the left side, you can see there are 3 levels of network. On the right side, there are 2 levels of network. So in this network, if in the first case, if node X want to talk to node Y, since they are both in the same level of network, so you can see their source address and destination address are of the same length. And there's no need to go outside of the level networks. They can directly talk with each other with their own short address. In another case, if node X want to talk to node N, so they are in a different subnetworks, and but their common level network is level 1 network. So in this case, node S need first to go out of its local level 2 network. You can see first it will go out, go through the LGR-B, level gateway router B. So level gateway router B will keep its own network prefix, which is a 16-bit bit long. So at this router, it will augment the source address with this prefix. So on the right side, you can see the example here. The source address changed. Then now the source address and the destination address have the same length. Then it can forward in the same level of network, and eventually it will reach the level gateway router E. And that node, because the destination prefix is no longer needed, then it's stripped off this prefix. Then only leave the node ID of the node N and forward into this lower level network. And then finally, node N receive this packet and with only the necessary part of the address. Next slide.
Okay, just quickly, well, we are already behind, well, the official time for the session has finished. So if you can quickly recap.
Yeah, okay, then next slide. And so you can, so yeah, so basically this is a address scheme to how we can truncate or use only the necessary part of the IP address. And we have a way to incrementally deploy it in current IPv6 bit network, because it only affects part of the edge network. And in the following slides, I also show that it's a relationship with current existing header compression schemes. So basically, it's orthogonal to those schemes. Those schemes can still apply, but this scheme alone is stateless and is applicable to all kinds of networks. So can you go to the last slides? I just want to show. Yeah. So we are looking for maybe next slides. We just skip this one. Yeah, looking for a collaboration and also future work suggestions, and also we'd like to find the best place to adopt this work, and also see if 6LO is interested to this work. Thank you.
Okay, so a quick comment from my side would be that it would be good to check how does your mechanism compare against other mechanisms like 6LoWPAN header compression or even CHIC header compression, for example, in terms of which would be the resulting header size after compression. So that would be good to know to better assess the mechanism.
Yeah. In previous slides, I actually have a brief summary for the comparison. You can look at that, but also I can give some other solid number on the actual saving of the overhead.
So the point would be to see if your mechanism would be able to outperform the existing mechanisms, or do something, or has some particular benefit that the existing mechanisms don't have. I think it would be good to discuss that.
Yeah, many benefits. Is applicable to many different network environments, and also have some other benefits. But in terms of overhead saving, I don't think it can compete with those header compression schemes, because those schemes are based on the context based header reduction compression techniques. We only concern the part of the address, and also we can apply the similar techniques to reduce the size of the other part of the header. But this is not main concern of this draft. Here we care only about the address, and also show its benefits to be applied in many other environments.
Okay, at some point the room will get closed. So I don't know if there's time for any very quick question or comment. Otherwise, we can continue the discussion on the mailing list. So
All right, thank you.
if there's no further comment or question, then let's end the session here. So thanks a lot to everyone for attending and contributing and making comments and presentations. Thanks a lot, and see you in the next meeting and on the mailing list.